Heyo! All right, guys, welcome to the last lesson of the semester. We're going to be finishing up chapter 34 on spherical refracting surfaces and thin lenses. Before we get into that, I just wanted to review mirrors. Okay, so these are spherical reflecting surfaces. Remember, our equation for spherical mirrors was 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length. And the focal length was half the distance of the radius of curvature, right? So 1 over f is equal to 2 over r. I also wanted to remind us about sort of the rules that go along with mirrors so that we can compare them with lenses. When the object faces a concave mirror, then we know that the radius of curvature and the focal length will both have positive values. On the other hand, when it faces a convex mirror, the radius of curvature, the focal length will both have negative values. And we also know that the image will always be negative. It'll always be a virtual image formed by a convex mirror. So we have that negative image distance. Additionally, where the images form, if for mirrors, when the image forms on the same side as the object, on the object side, it's a real image. And remember, a real image is associated with a positive image distance. When the object forms on the opposite side of the mirror, right, from the object, that's a virtual image, and virtual images are associated with a negative image distance. Okay, good. So that's our review of mirrors. Now let's see how that changes for refracting surfaces. So for refracting surfaces, this is where you have, glass or amber or plastic or something like that in a shape that refracts the light instead of reflecting it. Okay? Now, the first thing I want to talk about is single-sided refracting surfaces. So imagine you have, like a big chunk of glass, and there is one side that has a curve, right? It has some radius of curvature. It's either concave or convex. But for a single-sided refracting surface, this is going to be our expression. N1 over the object distance plus N2 over the image distance is equal to N2 minus N1 over the radius of curvature. Now those N's are the index of refraction of the materials, okay? N1 is going to be the index of refraction of whatever material the object is in, okay? That's the index of refraction on the object side. N2 is going to be the index of refraction on the opposite side of the object. So if you can imagine this, I'll kind of draw a little picture here. Remember in Jurassic Park, the first one? I don't know if you remember it or not. He had that little mosquito in the amber, right? So there's some object, the mosquito, right? And it's got its long, that doesn't look very good like a mosquito. Anyway, it's surrounded by amber, right? So the object is in amber. The amber, whatever the index of refraction of the amber is, will be N1, okay? And then out here on the opposite side, so here's the surface, right? Say it's facing this concave surface. Let's make this chunk bigger so it's more obvious. It's like a big chunk. The object is facing a concave surface, and out here, the air, when we're looking into it, that's going to be N2, the index of refraction of the air. Okay, so that's just a little illustration of sort of how we would work those things out. Now, the rules do change a little bit, right? We've studied what mirrors do, but refracting surfaces, we change a little, okay? So, these are the big differences. When on a refracting surface, when the object faces a concave surface, we're going to treat that radius of curvature as a negative value. Okay, so that's obviously different from mirrors. Okay, the other side of it is when the object faces a convex surface, that radius of curvature will be a positive value. Okay, now the other thing that changes between mirrors and refracting surfaces is where the object forms, where the image forms based on real and virtual. So now, a virtual image is still going to be associated with a negative image distance, and a real image is still going to be associated with a positive image distance. However, a real image forms on the opposite side of a refracting surface, okay? Virtual images for refracting surfaces form on the same side as the object, okay? That's a clear distinction and difference between what it was for mirrors, all right? Okay, got to keep those things straight. And we'll talk about it a little bit more when we get to lenses. All right, so let's look at thin lenses. So this was a single refracting surface. A lens will be two refracting surfaces, one on each side. All right, so let's take a look at that. Okay, so for thin lenses or for a double-sided refracting surface, we've got two different types. We've got a converging lens and a diverging lens. And essentially we're going to be just focused on lenses that are symmetrical on both sides. There may be some problems in there where you might have a flat side or something like that, but for our purposes here, we're talking about lenses that have symmetrical sides. So a converging lens brings in light rays and focuses it down to a particular point, a focal point. Whereas a diverging lens causes the light rays to diverge away and out, and it has what we call a virtual focal point. I'll try to illustrate that. Imagine that you have, light coming in, and it strikes these sides and it refracts in to the lens, and then it focuses down to a point. So this is like a magnifying glass, okay? It's going to cause a real focal point. We call this a real focal point. It will have a positive focal value, right? A diverging lens, on the other hand, the light rays come in and they refract out, and those refract the opposite way, and they diverge away. And if we make a ray tracing back, we would say it has a virtual focal point, right, which would have a negative value. So converging lenses have a positive focal length, which forms on the opposite side of the lens from the object. Diverging lenses have a negative focal length, and that focal length is on the same side as of the object. It's on the object side. Okay, so let's talk about diverging lenses first, real quickly. Diverging lenses, similarly to convex mirrors, diverging lenses can only form virtual images. Okay? Those virtual images will always have a negative image distance. Now, remember, we talked about refracting surfaces. Where do those virtual images form? The virtual images form on the object side. So it's on the same side as the object. Okay, virtual images form on the same side as the object. Now, converging lenses can form either real or virtual images depending on where the object is in relation to the focal length. Again, very similar to concave mirrors. If the object distance is greater than the focal length, then it will form a real image. Again, that real image has a positive image distance. Where do those real images form? They form on the opposite side of the lens from wherever the object is. However, if the object distance is less than the focal length, then the converging lens will form a virtual image, and that image will have a negative image distance, and those virtual images form on the same side as the object, right? They form on the object side of the lens. Okay. Now, how do we calculate all this stuff? Well, there's only the index of refraction of the lens itself, whatever it could be glass, it could be plexiglass, plastic, whatever it is. So there is the index of refraction of the lens, and we calculate all of these with this relationship: 1 over the object distance plus 1 over the image distance is equal to 1 over the focal length, which is equal to the index of refraction minus 1 times 1 over R1 minus 1 over R2. Okay, now let's talk about those real quick. R1 and R2 are the radii of curvature of the sides of the lens. R1 is the radius of curvature of the first side. So for a converging lens, R1 is measured here. It's from, if say our object is over here, right? This is a convex, right, side. And we said for lenses or for refracting surfaces, a convex radius of curvature will be positive. So R1 is positive. R2 is the second side. So the first side we get to is R1, the second side we get to is R2. It's going to have its radius of curvature over here, R2, and that's negative. Okay? So you can see, in order to get a positive focal length for the converging lens, we have 1 over a positive number minus 1 over a negative number, right? That minus a minus becomes a plus, so that gives us a positive focal length. However, for a diverging lens, this first side that we get to is R1, and it is concave, right? Concave has a negative radius of curvature for refracting surfaces. The second side we get to is convex. Its radius of curvature is over there. It would have a positive radius of curvature. And when we put these into this equation, right, we have a negative R1 minus a positive R2. That's how we end up with a negative focal length for diverging lenses. All right, the other things that we do in lenses are very similar to mirrors. We can talk about the magnification. That formula is the same. The magnification is going to be, at least the absolute value of magnification is the image height over the object height. Or we can do it in terms of the image distance and object distance. The magnification is the negative of the image distance over the object distance. Those formulas are the same both for mirrors and lenses. And it also, remember, the magnification is what tells us the orientation of the image. So a virtual image, which will always be associated with a negative image distance, will be upright, whereas a real image, which is always associated with a positive image distance, will be inverted. Okay, all right, I got a quick little video for you guys just to kind of show a converging lens. So take a look at that. Okay guys, so what we have here is a converging lens. Remember, for a converging lens, it can form real or virtual images depending on the distance of the object, right? If the object is outside the focal length of the lens, then it'll form a real image. So you can see this is a converging lens. It's a magnifying glass. You can even see some of the, the lettering on this pizza box that we have here. Obviously it's magnified, right? And so what I want to show you is we're going to form a image of the sun just by getting the proper focal length of our lens. And that is a real image of the sun right there, that very bright spot on our box. So remember, for Alice, can you come out of the sun, please? Thanks. For lenses, real images form on the opposite side of the lens from the object. So obviously the sun is over that way, and it's very far away. It's outside the focal length of our lens. And the real image forms on the other side of the object, right there, that very bright spot. What's cool about converging lenses, that's the focal point of our lens. We can also take all of that energy from the sun's rays that are coming in and converging down to that focal point, and we can utilize that energy with our ball of lint here. If I can focus this down just right, then we can actually start a fire there. Look at that. Okay. That's that real image of the sun, which is all that energy focused in, which is then burning that lint. Cool, huh? Check that out. So, Alice, stay out of the sun. Here, come down and show that. Isn't that there? So that's real images for you. All right. All right, so, and I recommend, like we did with mirrors, breaking it out in a table. Perhaps I'll do that on the sample problem. But if you have any questions, let me know. And I hope you have a great day. Take care.